Here's an overview. I would like to introduce myself first and then give a brief introduction, as I said, in the importance of the angle of attack for a fixed-wing plane. After that, the many measurement principles that could be used to measure such an angle. Then the version I chose and the sensor I built with wind tunnel test data and optimization potential, and a further outlook on what I'm going to do next. So first about me, my name is Jakober. I am working at the Institute of Automation at the University of Applied Sciences in northwestern of Switzerland. And I'm also part-time doing my master's studies in engineering, the profile of mechatronics and automation. And my PX4 journey started about 2 years ago when my friend Jakober came up to me and said, Daniel, when I get a new plane, I need to configure this, I need to tune the PID controllers, and that is too time-consuming, too complicated if you're not a flight engineer. Can we automate this? And then I thought, well, let's try. So I spent the 2 first semesters on auto-tuning of the fixed-wing attitude controller, until I discovered that Matteo Bresciani already did that better and faster, and therefore I had to switch topics. So then I went on modeling of the flight dynamics of a fixed-wing UAV in order to, after that, simulate my own plane and identify the parameters of my own plane in order to get the optimal configuration to get the best flight performance out of my plane. After getting a model with generic parameters of a fixed-wing plane, I noticed that in order to validate my model and to correctly identify my parameters, I somehow needed to get a true reference. So if I only took the measurement data that the PX4 is logging from his IMU and used that for identification, I'd most probably identify the model that is in PX4 and not necessarily the true model. So therefore, I decided to build or buy, if there was one available, an angle of attack sensor to get a true value of the angle of attack in flight. And that's what I'm going to be presenting to you now, and an outlook of my master's thesis that I'm going to be working on in the next year is I'm going to be identifying these parameters in order to simulate and optimize the flight dynamics and flight performance of my plane. So starting with the importance of the angle of attack. So on the top left corner, you see the general lift equation, and the lift is comprised of a half times the air density times the velocity squared times the wing surface area and the lift coefficient. The wing surface area shouldn't change much in flight, as the air density doesn't change that much either, so our main variables that define the lift is the airspeed and the lift coefficient. As the airspeed is only a scale, I'm going to be talking mostly about the lift coefficient that you can see on the right side. For a lift, there's a lift curve of a SM701 profile, where you can see in red that for an angle of attack of -5 degrees, we get no lift, and at about 20 degrees, we have the stalling of the plane. So now the question is, how is this angle of attack defined? On the bottom left, you can see that the wing chord line from the tip of the wing to the behind part, we draw a straight line, and reference to the oncoming wind is here shown as alpha, the angle of attack, that defines the coefficient of lift. But why is that a problem with traditionally IMU data, or why does every bigger plane have an angle of attack sensor and our small drones don't? Well, as I said before, the angle of attack is defined to the relative wind that our drone encounters. So as we can see here, it's not defined to the horizontal plane, but rather to the relative wind. But since the ratio of the relative wind, if you fly into an updraft fast enough, the ratio that the angle of attack changes isn't that big. So therefore, flying with an IMU with additional safety margins is more than enough. But if you really want to get all of your flight envelope used, you have to have a sensor that gets you the correct angle of attack. Next up, I'm having a video of a company that does measure these, the angle of attack, the angle of side slip, and the velocity. Let's see if we can skip a little bit of that. So this is not very interesting at the start. And I would like to draw your attention to the top right corner, where you can see the IMU and GPS estimate as indicated by a black cross, and the air data computer measurements as a red cross, and we can see there are significant deviances. And also below that there is the indicated airspeed through to an airspeed sensor and the GPS ground speed. There is to be noted that this is not a PX4 flight controller to my knowledge, so the PX4 could have better estimates, but to get really the true value, you would have to need an additional sensor, especially when you're flying close to the border of your flight envelope in some crazy maneuvers, or if you're trying to fly pretty slow and have a high angle of attack near the stall region. So let's get to the next slide. So how would I measure that? The most obvious reason that would come to mind when someone wants to measure the direction of the wind that it's coming from is a wind vane. And you can see that on the top right corner. The guys at ETH Zurich already did that, and it worked quite well, but there are also drawbacks to these mechanical systems. As further and foremost, the friction in the bearing cannot be neglected when you're flying in lower airspeeds. As when you're flying in lower airspeeds, the force that is acting on the wind vane is pretty small, and therefore the friction can't be neglected. And also these wind vanes have to be balanced out pretty good as to not get an offset in accelerated flight as when you're flying a curve or accelerating up or downwards. And also because they are mechanical, they have a significant time constant that limit the speed of the sensor, and they also could tend to oscillate. What are other measurement principles? We could also do it thermally with a hot wire that is put in the airstream, and therefore we can estimate the velocity through the convection of the airstream, and using 3 or more wires in different orientations, we could therefore calculate back the angle that the wind is coming from. We could also use acoustic systems, because the sound's traveling through the air depending on the wind, of course, and with multiple speakers and microphones we could also estimate or measure the wind that is where it's coming from. And last but not least, we have also pneumatic systems. I've shown in the bottom 2 various systems that Stefan Gaubisch used for identifying his glider plane. On the left we have a Conrad probe with 3 holes, and in getting the ratio with the differential pressure from the top to the middle tube and the bottom to the middle tube, you could also measure the angle of attack. This is only getting you a 2D picture of the wind vector, so you can only get one angle and the velocity that the wind is coming at you. And if you would like to have a 3D vector and also getting the angle of side slip as well, you would need a multi-hole probe with 5 holes or more. So what is there already available on the market? I did my research. I maybe didn't find everything, but what I found is there's on the bottom left a flight test boom comprised of a pitot tube and 2 wind vanes. And on the right, from the company that the video was before, a multi-hole probe with a corresponding air data controller. And the drawbacks of these systems is they might be good for bigger drones, for research drones that have excessive funding and everything, but for my small drone, they are way too expensive, as they cost 5,000 francs, which is about 1 to 1 to the dollar for this estimate, and even more depending on the calibration. And they weigh also 200 grams or more, including the controller that calculates the angle out of these measurements. So therefore, I had to resort to my own and build the sensor on my own, and this is what I came up with. I oriented myself on the multi-hole probe that Stefan Gaubisch used, and I have it here with me, as you can get about the scale of how big it is. We have 5 holes at the front with a hole diameter of 1 millimeter. And I also included a static port at about halfway on the shaft. So therefore, it seems like a combination of a standard pitot tube that you would use and a multi-hole probe to get the angles. This sensor and this probe was printed on a ProJet multi-jet printer with a plastic material and wax as support structure. This is not your ordinary hobby 3D printer, so I wouldn't recommend printing it on a standard FDM printer, as the quality would most probably not be enough. But using this multi-jet printer, as you will see in the wind tunnel results, it showed to be enough. And what is significant is that it's only 5 grams in weight, which helps me with my smaller drone, as I'm not adding too much weight to it. But that is only the probe head. I need to, of course, get the measurements of the different pressures. And therefore, I used the Sensirion SDP33 differential pressure sensor that is already been used in and integrated with PX4 for the airspeed measurement. And I purchased these through Drottec as finally already made product with additional tubes and casing. And therefore the problem arose that they all have the same I2C address. So I had to use an I2C multiplexer to not damage the sensors themselves. And therefore I used also a casing that is shown in red. I also have it here with me to see about the size of this sensor capsule that I built. This is because that the tubes are not in the free airstream and to reduce measurement noise, and also that everything is in a casing and doesn't get damaged from outside. And behind I have the connectors that I can connect to any controller or a I2C device to read out the data. This is in total 89 grams of weight, especially the big 3D printed parts take a huge role in that, but we are still significantly lighter than the already made products. So now I have a probe, I have a sensor capsule, but I have no idea what the measured pressures would look like. So therefore, I had to resort to our wind tunnel at our university for applied sciences, and I came up with 2 concepts. The first one you can see on the left, only using the angle of attack, where I mount my sensor in the middle of the wind tunnel and use a motor, shown in green on the bottom, to rotate it so that I can put the stagnation point on a line in the middle through the probe head, as indicated by the picture besides. Using another motor, also shown in green on the right side, I would be able to simulate different angles of attack at different angles of side slip and can put the stagnation point on every point at the spherical surface of the probe head. This is what I did. Here you can see the CAD drawings, where I used mostly 3D printed parts, as my budget was not that big, as I also said. You can see in blue the Sensirion sensors, and in red the adapter to the wind tunnel, and in gray the holder to get the probe head, the spherical head, exactly in coaxial to the turning axis so that the head won't be in a different, depending on the angle, won't be in a different position in the wind tunnel to get the influence of the wind tunnel out of my measurements. Here you can see it in action. Well, it's only a picture, not a video, but here you can see how it looked. There are two key things to notice. The first one is the wind anemometer in front to get an accurate wind measurement for my calibration. This is of course detachable as to not influence my readings. So I firstly put in what speed I would have to want and then detach the anemometer to measure. And the second thing that you can notice is my template I printed to exactly get my angles that I would like to measure at, because the motor I used wasn't able to put up with that much friction that I had in the wind tunnel. So therefore I did it manually, but still at the hopefully same exact measurements. So here are the measurements I took. There are, at the left, you can see the differential pressure from top to bottom, from the top to the bottom hole that I used to calibrate the angle, and also the differential pressure from the middle to the static port on the right, as I would expect it to look like as if I used an ordinary airspeed sensor with a pitot tube. The different colors symbolize the different wind speeds I was calibrating this at. I started with about 8 meters a second, where I oriented myself at the peaks for default parameters of about 10 meters a second for the lower speed. And then I went up until the friction didn't hold my holder anymore, and that was about at 16 meters a second. And we can clearly see that the differential pressure from top to bottom is dependent on the angle of attack, and the middle to static differential pressure is dependent on the velocity. But it's not entirely constant, as with increased angle of attack, the differential pressure changes, which can also be seen if you use a normal pitot tube to measure the wind velocity and put it at a bigger angle. The measured velocity won't be the real velocity anymore. I also used a simulation, so to see what I would like to see, what I would expect. You can see the simulation data as the line and my measurements as points. You can clearly see that these do not add up, and therefore I had to think about why do they not add up and what is wrong with my setup. And then it came to my mind that the Sensirion differential pressure sensor is very precise and has no zero-point drift, but it works different than other differential pressure sensors, as the standard differential pressure sensors use 2 chambers and measure the membrane in the middle to get the differential pressure, and the Sensirion sensor uses a bypass where the mass flow is measured of the air that gets through, and therefore we have an airflow in the sensor and also in the tubes. And because my tubes are only 1 millimeter in diameter, therefore I had a huge pressure drop in the probe itself. And then I found a paper from Sensirion to compensate this. I implemented this, and you can see the results on the right. It still does not add up. After asking back to Sensirion why doesn't it add up, they told me that these formula are only for laminar flow, and because my probe head is 3D printed, it of course isn't laminar anymore. So I stopped using a compensation and just worked on the measurement data, as I could see a clear dependency on the angle. The first thing I did is just a linear regression, and we can see that we already fit the data quite good, up to an angle of attack of 20 degrees. I chose this as because the differential pressures of over 20 degrees, they're not really linear anymore, and most of the airfoils that are being used already stall at 20 degrees of angle of attack. So if now the wind speed is already known, we could use this to get the slope and the static offset of our linear function. If you have an additional airspeed sensor, and therefore directly get our angle of attack through the differential pressure from the top to the bottom hole. What is interesting to notice is that all the lines cross at about 4 degrees and 0 differential pressure. But if you're thinking about the multi-hole probe, if the stagnation point is exactly between the top and the bottom hole, there of course is a differential pressure of 0, independent of which velocity the wind is coming at. But one might ask, why is it not at 0 degrees and at 4 degrees? It's not because I put my template 3 degrees off, but because the probe head was 3D printed. To get the wax that was used as support structure out, we had to heat the probe, and it just stood like this in the heating chamber, and therefore it bent, I believe, at about 4 degrees. So the probe head is just slightly bent, but everything else is as expected. This fit can, of course, be made better by using a quadratic function, as you would guess, of course, fits the data better, but has more computational load. But therefore, I chose, well, can we do better? Can we do more than 20 degrees angle of attack? And what do we do if we do not know the airspeed and we want to get rid of an additional airspeed sensor? So one cool thing that I saw is when I divided the differential pressure from top to bottom by the middle to static differential pressure, I could see that all the points are about lining up. And using this to get another quadratic function fit inside of it, we can already get, through these two differential pressures, an estimate for the angle of attack. But this is not what I found great, but I thought we could do even better by viewing the two differential pressures as independent variables, as seeing it on the x-axis, the differential pressure top to bottom, and on the y-axis, middle to static, and on the z-axis, the angle of attack. I could fit a 2D polynomial inside of it. It is, at the moment, it's degree 4, where I could mostly increase the precision I can measure the angle at. As we can see on the left side, because the range is pretty big, the bigger the angle of attack is, we have about an error of plus minus 2 degrees. And with a 2-degree polynomial, this error reduces significantly. So that's where I'm at the moment, and there is, of course, optimization potential. So what is there to do? First is improving the position of the holes. The sensor I'm using has a measurement range of 1,500 Pascal, and I'm only measuring 70. So therefore, improving the positions and enlarging the diameter of these holes, I can get much more precision out of the sensor because I'm using the full measurement range. Further optimization point is to remove the static pressure port, because in ordinary multi-hole probes, you wouldn't measure the differential pressure between the holes, but the absolute pressure of one hole, and using a calibration to get the airspeed and everything out of it. So that would be another possibility, so that I can even shrink my drone further, such that the static port isn't in the influence of the body of the airplane anymore. What is further to do is integrating the angle of side slip. As this multi-hole probe is the idea of a multi-hole probe, that is nothing I invented, that is already around for long. But using a 3D printed probe head, I haven't found any reference on, and I wanted to try it, and it looked reasonably good. So therefore, integrated the angle of side slip wouldn't be much of a problem. Also, increasing the velocity range shouldn't be much of a problem. And what I also want to do is using more advanced machine learning algorithms to get the calibrated sensor model, as this, what I already did is just a basic linear regression, and this could be optimized even further. And maybe the biggest optimization potential that I'm tackling right now is reducing the sensor capsule to a PCB. As the Sensirion differential pressure sensors are the world's smallest differential pressure sensors, at only 5 by 8 by 6 millimeters, I can get rid of all this red sensor capsule and put everything on a PCB and screw it right directly into the 3D printed part, as seen in the example picture on the right, and therefore reducing the weight significantly to about estimated 20 grams for the whole sensor. What I have on the left is the scheme for my PCB, what it should look like. I would have a microcontroller, for instance, STM32, but it hasn't been decided yet. But it should have at least 2 I2C buses, one to talk to the PIXHawk, the flight controller, and the other to read out all the sensors. And one could ask, why is there a 3-axis accelerometer added to this PCB? That is already thought of if you would be integrating your sensor into your drone. Instead of having to measure at which angle relative to your wing you mounted your sensor, I think about a calibration setup, as you would do with your standard IMU, that you would orient the plane relatively to the wings and let the probe figure it out itself, how it is oriented relative to your wing. So as to give a further outlook, what is going to be going on later is I expect to have a flight tested prototype by the end of 2023, at the end of this year, with about 20% of the cost of a comparable system that I found and about 20% of the weight of comparable systems. These numbers could potentially even go down. This is just a rough estimation, and this would be best suited for lightweight fixed-wing UAV with slow airspeeds. As in slow airspeeds, the wind vane, the pneumatic systems outweigh the wind vanes. And what is there also to do is integration into PX4. As if you can measure the angle of attack and the angle of side slip, you could also fuse that with the estimation that the PX4 has internally and therefore improve flight control performance, and also add redundancy to the attitude estimation as to get more safety. I also don't want to miss this opportunity to say thank you, especially to Jörg Keller, who is my professor and advisor in my master studies, as he helped me with very much of my problems. Also Jakob Strebel, who brought me into PX4 and is always open to help. And also Adrian Eckenberger, who's my go-to guy to fly my bigger drones where I'm too afraid to fly them myself. And also, of course, thank you to the Drone Code Foundation, Linux Foundation, and all of you for having me here. If there are any questions, I'll be open to answer questions. If you would like to get back at me, I'll be here all weekend. And you can also get at me at the Discord, email, phone, or else. Thank you. Yes, question at the back?
In your researching experience, do you think slower, say we got perfect data, do you think slower, lighter weight UAVs, do they have the precision to fly at the demanded angles of attack?
Well, so you're asking about the control performance, or?
Yeah.
I haven't been researching much into control performance. I would reference you to the guys from Arterion, as they're very much more experienced than me. But I believe if we have an accurate measurement of the angles, we could improve controller performance further. Yes?
So the 5-port solution with 5 modes is a standard stencil for getting differential measurements in both principal axes and the middle. Do you think if you have more ports, you could better solve for the side slip and angle of attack? Or would there be no benefit?
Yes, I believe that if I had more holes, I would be more precise. Well, it depends. I've seen from standard multi-hole probes, the 5-hole probe already is sufficient enough in a smaller angular range as to, so let's say, plus minus 20 or 30 degrees. But if you want to get beyond that, you would have to have more holes, if you have a bigger angle of attack, some of the holes might already be in the stall of the spherical head and therefore not producing accurate measurements. Yes?
You mentioned that the model you initially developed didn't fit as well with your data. Did the model contain temperature elements? Because I would expect that when you fit a model to data, you have no temperature variation. And as you do, your lift coefficients are dependent on your density, which changes with temperature. Temperature play a huge role into a model that's fitted primarily to data. What are your thoughts on temperature development and general concept?
Well, the formula I used to simulate my expected differential pressure didn't contain any temperature coefficients. As I got this out of a paper where they analyzed the pressure. Well, I have to reformulate my answer. It integrated some temperature performance, as the formula I used only was for the coefficient and not the absolute pressure. But concerning the whole temperature-depending behavior, the Sensirion differential pressures have an integrated temperature compensation. As they are measuring the mass flow thermally, they can already compensate for these temperature deviations, and therefore I expect the temperature the pressure differential they give to me as a constant over a temperature range. But it could possibly be that my sensor model in my first simulation would be off because of the temperature changes and the estimated air density I used. That's right. So if there aren't any more questions, I'd like to thank you for your attendance, and let's get to eating.